Hi everybody, we're moving into Chapter 9, and Chapter 9 is dealing with two different types of functions: exponential functions and logarithmic functions. We'll find out as we move through the sections in Chapter 9 that there is a relationship between those two types of functions. They are in fact inverse functions, and all of that will be covered as we move from one section to another in Chapter 9. In 9.1, we begin by looking at exponential functions. Now, we've looked at a lot of different types of functions. An exponential function is an equation where the exponent in the function is a variable. And as a matter of fact, that variable is known as the domain, because ordinarily it's going to be the variable x that's going to be positioned in the exponent position. The standard form of an exponential function that we're going to be dealing with primarily in 9.1 is f of x is equal to b to the x. Notice, an exponential function is an equation, like any other function is able to be written as, where the variable x is in the exponent position. That's why it's called an exponential function. Now let's just define a few things about this exponential function that's primarily written in standard form. The b is the base, and the base is any number that is greater than 0, but the base b cannot be equal to 1. So about the b cannot be negative. The b must be greater than 0, but one restriction: b cannot be equal to 1. Because 1, if it were the base taken to any exponent value, would remain 1. So b is not able to be equal to 1. The variable x, yes, it is called the domain. The variable x, functioning as an exponent, is able to be any real number. I express that in interval notation. Now, the primary focus in 9.1 is to take some exponential functions. We're going to be doing 3 of them, but 2 of the 3 are going to be written in the form that we've already discussed. And the first one that we're going to look at is f of x is equal to 3 to the x. The 3 is the base. Notice that it is greater than 0, and it does not equal 1. Now, our objective is to take this function and graph it on a coordinate plane. And there is no specialized technique for doing the graphing. We ordinarily just pick values, small enough values, that when we get the completed ordered pairs, we can accommodate those ordered pairs on a reasonable looking coordinate plane. So ordinarily the directions in the book for 9.1 are going to say, let the values of the domain, let the values of x commence with -2, then -1, then 0, then 1, and then 2. Because if we were to allow in this function, if we were to allow x to be a -3, +3, -4, +4, we wouldn't have enough room on the coordinate plane to plot the points, because the numbers would either be so very, very small or so very, very big. So the values that we choose for x are primarily based on how big or what the size of the base of our function is. So you'll ordinarily be told on the examples that you'll be doing on the assignment to allow the values of x to be probably this segment of domain right in here. Now, we're going to find the values of f of x, and remember f of x is the same thing as y. This is domain, this is range. Now, because f of x is equal to 3 to the x, I put 3 to the x right here so it would be just a little bit easier to come up with our answer. So if you're ready, I'm ready. Here we go. If x is equal to -2, and we want to find the value of y, then we're going to substitute -2 in place of x, and I'll kind of do that right here for a moment. I'm going to bring down that 3 and put that x value of -2 there. Now we can't make any sense out of 3 to the -2 because we're dealing with a negative exponent. So we need to reciprocate that base 1 over 3, and that gives us then the opportunity to change that exponent to a +2, and 1 over 3 squared would be equal to 1/9. I'll just kind of circle him. He's the y when x is -2. Let's go to the second one. 3 to the -1st. Well, we can't have a negative exponent, so we will as well reciprocate that base. We can change then that exponent to a +1, and that is simply 1/3. If x is 0, well then we'll have 3 to the 0, and we know that 3 to the 0 is 1. And if x is 1, we'll have 3 to the 1, and that is 3. And if x is 2, that would be 3 to the 2nd, or 9. These are the corresponding range values for those domain values. Now we're going to come along and show the graph of this. And I think we'll have enough room to do this. Let's see if we can plot these. Let's go ahead and start with if x is -2, y is 1/9. Now we can only come so close. If x is -2, then y is going to be just above the x-axis. It's not going to touch it. Just so that you can see that point. It might be a little bit difficult, but if Kristen can zoom in there just a little bit so it just kind of shows up. I'm off, but it's close enough. If x is -1, y would be 1/3. If x is -1, then we're going to go up just a trifle more, about 1/3 of the distance up. There's the first point. That's the most recent one that we did. If x is 0, y is 1. And if x is 1, y is 3. If x is 1, we'll go up 3. And if x is 2, you'll see how it just increases rapidly because it's an exponential function. If x is 2, y is going to be all the way up here to 9. And those are enough of the points that we're going to do. And then we connect them, and let's see if we can just kind of swing this down, so to speak. Swing it on down. That is a typical looking graph of an exponential function. Things increase rapidly, or things might decrease rapidly. It's a rapid climb. Sometimes it's very steep, somewhat like this is, or sometimes it can be a little bit flattened out, but this is a typical looking exponential function graph. We'll just kind of leave that there for a second because we're going to come back to it when we talk about the characteristics of this type of a function. So that's the graph of f of x is equal to 3 to the x. Now we're going to come over to number 2. I've got such limited space that I'm dealing with here. So we'll go to number 2. And it's f of x, or y, is equal to a base of 1/3 to the x. Now notice that base. That base is greater than 0, but it is not equal to 1, but it is greater than 0. It's a positive base. And the value of x is in the exponent position. That's what makes it an exponential function. Now, if we were to evaluate this function using this base of 1/3, and I came over here like I've already got this t-chart ready, and I'm letting x be -2, -1, 0, 1, and 2, it would be time consuming to substitute those numbers in place of this range value of 1/3 to the x. It'd be somewhat time consuming to come up with the values of y. Not impossible, but time consuming. So there is a primary reason why I selected this function where the base is greater than 0, but it is less than 1. Remember, the first one that we did was greater than 0, and it was greater than 1. This one has a base greater than 0, but it's less than 1. And we'll notice something different about its graph when we get it up there. But in terms of working with this, it would be much, much easier to come up with values of y if we were to somehow be able to take that base and make it become an integer, a rational number, an integer as opposed to that fraction. And we can do that by making use, really, of the rule of negative exponents. Now, you heard me say negative exponents. There's no negative exponent up there, but there will be if we do the following, and I'm going to do it. F of x is equal to, if we take this base, folks, if we take that base of 1/3 and invert it, flip it over, invert it, and make it 3, 3 over 1 is 3, then we'll have to change the sign of that exponent and make it a -1x. And this function, written in this fashion, without having to deal with the 1/3, is a much easier function to deal with. They're the same. It's just that we won't have to monkey around with a base of 1/3. So I'm just going to kind of stick up here this. 3 to the -x. And so let's start with x is equal to -2. Now we want to be careful. That negative sign right up there, that's not the sign of that negative on that -2. So when we substitute it, we're going to have 3, bring down that opposite sign right there, and then the value of x is -2. Well, the opposite of -2, or a negative times a negative, would make that 3 to the second, and 3 to the second would be 9. So when x is -2, y is 9. Let's go to x is -1. That would be 3. Bring down that opposite sign. Then make a tuck and put that -1 in there. Two negatives make a positive. That would make it 3 to the 1, or in essence, 3. If x is 0, bring down that 3. Doesn't matter if you bring him down. It doesn't matter if you bring down that opposite sign. You're going to put a 0 there. 0 is an unsigned number, so it's still 3 to the 0. There's no such thing as 3 to the -0. 3 to the 0, that's 1. And then the fourth one. Bring down that 3. Bring down that opposite sign, and to the right of that opposite sign, let's put the value of x. We have 3 to the negative first. We'll have to make use of the rule of negative exponents. And the rule of negative exponents will make that 1 over 3, and that would be the value of him. And then finally here, it would be 3 to the -2. That would become 1 over 3 to the 2nd, which would be 1/9. And now if we can plot this as well. Now I'll try to keep myself out of the way because I'm way over here on the right-hand side. So let's begin with this. If x is -2, then y has to be 9. So I'm going to have to kind of move in front of you a bit. If x is -2, then y is going to be all the way up here to 9. I'm going to be off on things right here, but let's just say it's there. If x is -1, then y is going to be 3. If x is -1, y is up 3. If x is 0, y is 1. You can already see how the movement of that curve is going to go. If x is 1, the value of y is 1/3. If x is 1, we'll go up about 1/3 of the way up in that little increment right there. That's close enough. And then if x is 2, y is going to be 1/9, very close to the x-axis, but no, it doesn't touch it. 0.1, 2, 3, 4, 5, and we make that curve. So we'll try to spin that in this way. Kind of comes down. Curve. And there's the graph of the exponential function where the base is positive, it's greater than 0, but it is less than 1. And the first one that we did, I know I'm repeating myself, this was the graph of the function where the base was greater than 0, it must be, but it is greater than 1. Now, I want to kind of stop for a moment after doing those two graphs, and I want to point out some of the key characteristics about the standard form of an exponential function. F of x is equal to b to the x. I want to be very clear before we show you these characteristics. These characteristics are only going to fit this model right here. It's not going to fit a model where the exponent might contain a variable, but it might have other information in the exponent in addition to that x. These characteristics that we're going to share are exclusively for this specific form of an exponential function. Okay? And here is the first of 5 characteristics, and I'll just kind of hold them up because, to be honest with you, I ran out of tape. And I don't know where I was going to put them, so I thought I would just show them to you. Characteristic number 1 of f of x is equal to b to the x. The domain for all of these types of functions will be the set of real numbers. And the range will be any real number that is greater than 0. Not equal to 0, greater than 0. Any positive number greater than 0. Now, let me just kind of put the sheet of paper down, and let's look at both of these, or let's look at this one. It mentions that the domain is all real numbers. You see this graph on this wing is going to keep going and going and going and going. It is never going to touch the x-axis, but it's going to continue to go. And this one is going to, on the right-hand side, it's going to continue to move up and out and out and out. If you were to take all of the points on this graph and bring them down to the x-axis that fits the domain, the entire x-axis would be filled up. The same for that second one. If you were to bring all of those points down, it would fill the entire x-axis. The domain is the entire set of real numbers. The range is any real number greater than 0. You see, let's just use this one. That's going to be the same over there. If you were to take, I don't care how far this moves to the left, it's never going to touch the x-axis. If you were to move it over to the y-axis, it will start with the very, very first number that is greater than 0. It will not be 0. It will be the very first number that will be greater than 0. And you see, folks, all of these points that will continue to go out, if you move them over to the y-axis, it will fill the rest of the y-axis up. So that's characteristic number 1. You have the opportunity to pause. You have the opportunity to write it down on a sheet of paper. Characteristic number 2. For all exponential functions that are written in the form of f of x is equal to b to the x, all of these graphs will intersect the y-axis at 0, 1. In other words, the y-intercept of all of these graphs will be 0, 1. 0, 1. 0, 1. That is a definitive characteristic. Y-intercept, 0, 1. Characteristic number 3. If b is greater than 1, b is greater than 1, we're looking at that graph. If b is greater than 1, the graph goes up to the right. You bet your boots it is. It's going up as you move to the right. It's going up to the right. As x increases, y will increase. When the value of the base is greater than 1, you will have what's known as an increasing function. An increasing function is one where, as your value of x increases, as the value of x increases, the value of y will increase as well. As x increases, y increases. So I think we can make this point about characteristic number 3. Whenever your base is greater than 1, the graph will always be representative of that kind of a look to the left of that board. It will be an increasing function. As x increases, y will increase. Characteristic number 4. If the value of b is less than 1, and greater than 0, which it must be. If it's greater than 0 but less than 1, the graph will go down to the right. And that one that we just finished off on, number 2, that is a decreasing function. It moves down to the right. And why does it move down to the right? Because its base of 1/3 is less than 1, but at the same time greater than 0. And because it's called a decreasing function, that sort of indicates as the value of x increases, the value of y decreases. As we increase the value of x, as you allow x to increase, the value of y is going to decrease. It's going to get smaller. That's characteristic number 4. And finally, the 5th characteristic. The graph of f of x is equal to b to the x will approach but does not touch the x-axis. On both of those, the graphs approach the x-axis, but it never will touch the x-axis. The x-axis, or y to the 0, the x-axis, or y to the 0, is called a horizontal asymptote. People, an asymptote is a line that the graph will never touch. It will get close to it, but it will never touch it. The graph of these two has a horizontal asymptote. The graph will approach the x-axis on both of those, but it will never intersect it. It will never touch it. Those are the 5 characteristics of this particular type of graph. And we're just going to kind of close off 9.1 right now. If we have a little bit of time, maybe on the next video, I can start off and show you a 3rd example before we move into the content of 9.2. But I wanted to get those out to you at this point in time. Now you take care of yourself, and we'll climb our way through this chapter 9 and get to the key things that we have to do. We'll say goodbye for now. You take care of yourself.